The National Electrical Code, or NEC, does not provide a specific definition for power utilization load. However, based on the context of the referenced article, it can be inferred that a power utilization load is a device or equipment that consumes electrical power to perform a specific task. Examples of such devices might be motors, heaters, lighting, and power tools. The devices that use current at any voltage are considered a power utilization load. Therefore, devices such as solenoids, process transmitters, and switches that consume electrical power would fall under the category of power utilization loads. The bonding jumper around liquid flexible metal conduit, or LFMC, is only required if the load is a power utilization load. Since solenoids, process transmitters, and switches are not typically considered heavy power utilization loads, the bonding jumper may be omitted if certain conditions are met. These conditions are: firstly, the LFMC is 6 feet or less in length. Secondly, the overcurrent protection, or OCP, is 10 amps or less. Therefore, the wiring method using rigid metal conduit, or RMC, to about 3 feet from the field device, then LFMC to a conduit seal and field device without a bonding jumper is correct, provided the previously mentioned conditions are met. It is important to note that the requirements for bonding jumpers around LFMC may vary depending on the specific location and application. Consider the installation in a refinery. It is recommended to consult with a qualified electrician or electrical engineer to ensure compliance with all applicable codes and safety standards. Let's further elaborate on the concepts discussed. Firstly, let's delve deeper into the definition of a power utilization load. While the NEC doesn't explicitly define this term, its meaning can be derived from the context in which it's used. Think of it as any electrical device designed to convert electrical energy into another form of energy to perform a specific function. This could be mechanical energy in the case of a motor, thermal energy in the case of a heater, or light energy in the case of a lamp. The key is that the device actively consumes power to achieve its intended purpose. Now, let's consider some examples to clarify this further. A large motor driving a pump in a refinery would undoubtedly be considered a power utilization load. It draws a significant amount of current to generate mechanical energy, which in turn moves the fluid. Similarly, an electric heater used to maintain the temperature of a process vessel would also fall into this category. It converts electrical energy into heat energy, requiring a substantial power draw. However, not all electrical devices are considered power utilization loads. A simple switch, for example, doesn't consume power in the same way. It merely acts as a conductor, opening or closing a circuit to control the flow of electricity to another device. While the switch itself might have a minimal current flow through it, its primary function isn't to convert electrical energy into another form. Similarly, a low-power sensor or transmitter, while it does require some electrical power to operate, might not be classified as a heavy power utilization load, especially if its current draw is relatively small. This brings us to the importance of the overcurrent protection rating. The 10 amp limit specified in the NEC is a crucial factor in determining whether a bonding jumper is required around the LFMC. The purpose of the overcurrent protection device, such as a circuit breaker or fuse, is to protect the circuit from excessive current flow that could lead to overheating, insulation damage, or even a fire. By limiting the overcurrent protection to 10 amps, the NEC is essentially reducing the risk of a high fault current flowing through the LFMC in the event of a ground fault. This is why the bonding jumper can be omitted in certain cases, as the risk of a dangerous voltage potential developing on the LFMC is minimized. Now let's examine the role of the LFMC itself. LFMC is a type of flexible metal conduit that provides mechanical protection for electrical conductors while also allowing for movement and flexibility in the wiring system. It's commonly used in situations where rigid conduit is impractical or impossible to install, such as connecting to vibrating equipment or navigating tight spaces. However, LFMC is not as effective as rigid conduit in providing a low impedance path for ground fault current. This is because LFMC has a higher resistance than rigid conduit, which means that a larger voltage drop can occur along its length during a ground fault. This voltage drop can create a shock hazard if someone comes into contact with the LFMC. This is where the bonding jumper comes into play. A bonding jumper is a conductor that is installed around the LFMC to provide a low impedance path for ground fault current. By bypassing the LFMC, the bonding jumper ensures that the voltage potential on the LFMC remains close to ground potential, minimizing the risk of electric shock. However, as we've discussed, the bonding jumper is not always required. When the LFMC is short, the overcurrent protection is low, and the load is not a heavy power utilization load, the risk of a dangerous voltage potential developing on the LFMC is reduced, and the bonding jumper can be omitted. It's important to emphasize that these rules are based on specific conditions and are intended to provide a safe and reliable electrical installation. Now let's address the specific wiring method described. The use of RMC to within 3 feet of the field device, followed by LFMC to the conduit seal and field device, is a common practice in industrial settings. RMC provides excellent mechanical protection and a low impedance ground path, while LFMC allows for the necessary flexibility to connect to the device. The key is to ensure that all components are properly installed to meet the requirements of the NEC. The conduit seal is an important part of the wiring system, especially in hazardous locations. Its purpose is to prevent the migration of flammable gases or vapors from one area to another. The conduit seal must be installed correctly and filled with an approved sealing compound to maintain its integrity. The union is a fitting that allows the conduit to be disconnected without having to rotate the entire conduit run. This can be useful for maintenance or repair purposes. The field device itself must be properly grounded to ensure that any fault current can safely return to the source. This grounding can be achieved through a dedicated grounding conductor or through the metal enclosure of the device. In the absence of a bonding jumper around the LFMC, it's even more critical to ensure that the RMC is properly grounded and that all connections are tight and secure. This will help to minimize the impedance of the ground fault path and reduce the risk of a voltage potential developing on the LFMC. Finally, it's worth reiterating the importance of consulting with a qualified electrician or electrical engineer. Electrical codes and standards can be complex and are subject to change. A qualified professional can assess the specific application and ensure that the wiring system meets all applicable requirements. This is especially important in a refinery environment, where the presence of flammable materials adds an extra layer of complexity. In summary, understanding the definition of power utilization load, the role of overcurrent protection, and the function of the bonding jumper are all essential for ensuring a safe and reliable electrical installation. By following the requirements of the NEC and consulting with qualified professionals, electrical hazards can be minimized and the safety of personnel and equipment can be protected. Furthermore, let's discuss the practical implications of these concepts in a refinery setting. Refineries are inherently hazardous environments due to the presence of flammable liquids and gases. Electrical equipment used in these locations must be designed and installed to minimize the risk of ignition. The NEC has specific requirements for electrical installations in hazardous locations, which are classified based on the type and concentration of flammable materials present. These classifications include Class I, Division 1 Class I, Division 2, and so on. The wiring methods used in a particular location must be appropriate for the hazard classification. For example, in a Class I, Division 1 location, all electrical equipment must be explosion-proof, meaning that it is designed to contain any internal explosion and prevent it from igniting the surrounding atmosphere. In a Class I, Division 2 location, equipment can be either explosion-proof or intrinsically safe, meaning that it is designed to operate with very low energy levels that are insufficient to ignite flammable materials. The use of RMC and LFMC in a refinery is a common practice, as these wiring methods provide mechanical protection and can be used in hazardous locations when properly installed. However, it's crucial to ensure that all fittings and components are rated for the specific hazard classification. For example, explosion-proof fittings must be used in Class I, Division 1 locations. The conduit seals mentioned earlier are particularly important in preventing the migration of flammable materials from one area to another. These seals must be installed at specific locations, such as where conduit enters or leaves a hazardous location, and must be filled with an approved sealing compound. The sealing compound creates a barrier that prevents the passage of gases or vapors. In addition to the wiring method, grounding is also critical in a refinery environment. Proper grounding helps to minimize the risk of static electricity buildup, which can be a source of ignition. All metal equipment, including conduit, enclosures, and machinery, must be properly grounded to provide a low impedance path for fault current. This grounding can be achieved through a dedicated grounding conductor or through the metal structure of the building. Regular inspections and maintenance are essential for ensuring the continued safety of electrical installations in refineries. These inspections should include checking for loose connections, damaged wiring, and corroded components. Any deficiencies should be corrected promptly to prevent potential hazards. It's also important to train personnel on the proper use and maintenance of electrical equipment. This training should include information on the hazards of electricity, the importance of grounding, and the proper procedures for working on electrical systems. In summary, electrical safety in refineries requires a comprehensive approach that includes proper wiring methods, grounding, bonding, and regular inspections and maintenance. By following the requirements of the NEC and consulting with qualified professionals, the risk of electrical hazards can be minimized and the safety of personnel and equipment can be protected. Finally, let's consider some additional factors that may influence the decision of whether or not to install a bonding jumper around LFMC. One factor is the presence of sensitive electronic equipment. In some cases, even a small voltage potential on the LFMC can interfere with the operation of sensitive electronic devices. In these situations, it may be necessary to install a bonding jumper to ensure that the LFMC remains at ground potential. Another factor is the potential for corrosion. In corrosive environments, the LFMC may be subject to corrosion, which can increase its resistance and reduce its effectiveness as a ground path. In these situations, a bonding jumper can provide a more reliable ground path and help to prevent the buildup of voltage potential on the LFMC. The specific requirements of the local electrical inspector should also be taken into consideration. Electrical inspectors have the authority to interpret the NEC and may have specific requirements for bonding jumpers in certain situations. It's always a good idea to consult with the local electrical inspector before starting any electrical work to ensure that the installation meets all applicable requirements. In addition to the NEC, other codes and standards may also apply. For example, the National Fire Protection Association, or NFPA, publishes standards on electrical safety in industrial occupancies, such as NFPA 70E. These standards provide guidance on safe work practices and may include additional requirements for bonding and grounding. The manufacturer's instructions for the LFMC and fittings should also be followed. These instructions may include specific recommendations for bonding and grounding. It's important to note that the absence of a bonding jumper does not necessarily mean that the LFMC is not grounded. The LFMC is typically grounded through its connection to the RNC and the equipment grounding conductor. However, the bonding jumper provides an additional level of protection by ensuring that the LFMC remains at ground potential even if the connection to the RNC becomes compromised. In conclusion, the decision of whether or not to install a bonding jumper around LFMC is a complex one that depends on a variety of factors. These factors include the type of load, the overcurrent protection rating, the length of the LFMC, the presence of sensitive electronic equipment, the potential for corrosion, the requirements of the local electrical inspector, and the applicable codes and standards. By carefully considering all of these factors, electrical professionals can make informed decisions that ensure the safety and reliability of electrical installations. And remember, when in doubt, it's always best to err on the side of caution and install a bonding jumper.